Welcome everyone to today's video on the rate determining step in pre-equilibrium approximations. So in the previous video we talked about the steady state approximation. The rate determining step in pre-equilibrium approximations are the other approximations that we'll use in solving different reaction mechanisms in future videos. So after this video, all the next set of videos are all going to be about specific examples of reaction mechanisms and things of that nature. Photochemistry, polymerization, enzyme reactions, other things like that. So the rate determining step approximation is a fairly kind of simple one, right? And basically states that typically for most chemical reactions, right, there's some step in the mechanism, some specific reaction that's extremely slow compared to the others. That takes a lot of time compared to all the other ones, right? And we call that step the rate determining step, right? And it's, you know, given that name because the idea is it's what is determining the overall rate for the chemical reaction, right? And so, for example, right, if you're in a large crowded room and the fire alarm goes off, right, everyone might be able to get quickly to the door, but it can take a very long time to get through that door, right, to get out. So the rate determining step to how fast you can get out of that room after the fire alarm has gone off is how quickly can you get through the door. Not how quickly can you get to the door, but how quickly can you get through, right? Because that's kind of the rate determining step. And so, so that is the idea of approximation, right? Is that you have some reaction mechanism, right, that there's some step on that mechanism that has the largest kind of activation barrier, right? If I think of kind of my activation barriers here, right, you know, there's this barrier here, there's one here and one here, right? This first barrier is much greater, so it's the rate determining step. It's what's going to determine how fast or how slow your reaction goes, right? And so, right, so then we can think of, like, say, for this example, right, I have this overall chemical reaction that has this mechanism, right, and the first step is the slow step, right, and what is the rate law then for this mechanism, right? Well, we know the rate law for the first reaction is the rate equals K1, concentration of B, times concentration of F, right? Well, and B and F are reactants, right? You can see that based off of this, right? So B and F are reactants, right? That is my rate law for that first step, right? Well, since that first step is the slow step, I'm going to say, right, this is the rate law for step one, right? I'm going to approximate that this is just the rate for my reaction, right? And that's it. And then that is my rate determining step. That is, right, the approximation that's being done. It's saying the rate of the reaction is just equal to the rate law, right? of the slowest step, right? And so the main question is that slowest step, right, going to be one that has intermediates in its rate law or not? If it does, then we maybe need to use other approximations to get the final one. Okay. So the other set of approximations is things like the pre-equilibrium approximation, right? So let's assume I have this reaction here. I have A going to I and I going to P, but I have this first reaction can be an equilibrium where I can go back to A, right? So let's assume that in this reaction, this step is the slow step, right? Potentially the rate determining step, if you will. And this step is very fast and reaches equilibrium, right? Right? And so the idea is because the first reaction here is so much faster, right, equilibrium gets established and is maintained as the reaction is going on, right? Because as the reaction is going on, I lose some amount of I, but if that equilibrium establishes itself very quickly, then once I lose some I, I'm going to gain some of that back and re-establish my equilibrium in that first reaction. So the idea is I'm always at equilibrium as the reaction is going, okay? And this only works when that step after equilibrium is significantly slow, right? If I is being consumed very quickly compared to how fast it's being formed, then I'm never going to be able to establish equilibrium, right? And so this only works if the step after the equilibrium step is very slow, okay? And if that is, then we can use the pre-equilibrium approximation, which what that's saying is that in this reaction, right, again, if I'm assuming the second step is slow, right, the rate of formation of P, which is related with the rate of the reaction, right, it's just equal to K2 times I. Well, I is an intermediate, but I know if this establishes an equilibrium, right, this is at equilibrium, right, well, I know that the rate constant, the equilibrium constant K, which just equals the concentration of I divided by the concentration of A squared, right, given the mechanism here, right, it holds true. I'm at equilibrium, so this is true. And so therefore I can use that equilibrium constant expression to solve for I, to say, well, concentration of I just equals capital K times concentration of A squared, okay? Where capital K, again, we talked about this in the previous video, right, is just K1 over K minus 1, right? So equilibrium constant for a reaction at equilibrium, the equilibrium constant is just the rate constant of the forward reaction divided by the rate constant of the reverse reaction, okay? So that is what the equilibrium constant comes out to be, okay? For some elementary reaction that's at equilibrium, okay? And so yeah, so then we can just plug this in back up into here, right, to get the final expression K1, K2 divided by K minus 1 times concentration of A squared, right, is equal to the change in concentration of P as a function of time, which does not depend on intermediates anymore, right? And so this gives me a very simple way to be able to get rid of this dependence upon any intermediates, right? And this shows me what the rate of my reaction is, okay? And so that is the rate determining step and the pre-equilibrium approximation. Now the rate determining step doesn't have to be coupled with the pre-equilibrium approximation, but the pre-equilibrium approximation needs sort of this rate determining step, if you will, right? This slow step to occur after equilibrium, okay? Because again, if the slow step is not occurring after equilibrium, then you're not going to get an equilibrium established, okay? So we need those two things kind of together for the pre-equilibrium approximation, but you could have a rate determining step and not any equilibrium reactions, right, and still use something like the steady state approximation if you need to and stuff like that, okay? And so that is our set of approximations that we use to help solve for rate laws and for given mechanisms, and so we'll use these over and over and over and over again when we talk about more and more different mechanisms, okay, and reaction examples and kinetic examples.